on Tuesday, right? Couple of additional problems for you to try if you wanted to have some challenging sequences. Did I say it's due today? I think I did, right? So if you have it, I'll take it now. If you don't have it, it's okay. It's optional. It's an extra credit assignment. Were they fun? Did you enjoy those?
I'll keep working on it later.
Okay.
I didn't find out about it until 10 minutes ago.
Okay. Anyone else? All right. Thank you. All right. So let's get going here. We have a lot to do. We are going to continue with 8.1 and try and get into we are getting to 8.2 today. So the main idea from last class towards the end was this idea of the limit of a sequence. So if we have the formula for a sequence and we want to know what happens to the sequence as you keep going out forever, then we have to take the limit of that sequence as n goes to infinity. And if that limit gives us a number, L, then we will say that the sequence converges to L. And if it doesn't go to a number, it does anything other than going to a number, then we will say that the sequence diverges. All right? And I showed you after that a couple of examples, and we started to use a theorem that said that, well, if we're ever looking at a sequence and we're having trouble with it, we can convert the sequence to a function of x, and then that allows us to use L'Hopital's rule and anything else like that to evaluate the limit. And that's where we stopped. So I want to do another example, this one right here. It's a sub n equals sine n over n squared. And the question is, does this converge or diverge? So does this converge or diverge? And I said last class, instead of doing that, I'm going to put C or D, right? Like that instead of writing that over and over. All right, well, let's see. If I try and take the limit as n goes to infinity of sine n over n squared, then what happens here as n goes to infinity is, well, the bottom goes to infinity, right? N squared gets bigger and bigger and bigger, so the bottom goes to infinity. But what does sine of n do? So you have to think about what it looks like, right? What does this sequence look like? So ignore the n squared. What does sine n look like? Well, if I plug in 1, I get sine of 1, right? What's sine of 1? I don't know. Get your calculator out, right? You get an answer. Then you have to do sine of 2, then 3, then 4. See, these are not those nice, it's not like pi or 2 pi or pi over 2. These aren't nice numbers, right? So what's going to happen is you're going to get kind of like a sine curve, but it's just dots along the sine curve in different places, and it's going to look all scattered, right? Just like a bunch of dots all over the place. And so you can't tell me that that's headed to any particular number. It's not headed to 1, it's not headed to -1, it's not headed to 0. It's just kind of like, you know, like salt and pepper, or pepper just kind of scattered all over the place, right? So what would we say then the top is doing? It's headed to, well, that limit doesn't exist. Okay, the top, this limit does not exist. Does not exist. And that is not something we can just look at and get an answer, because we need either like 0 over 0 or infinity over infinity to do L'Hopital. So this is still an indeterminate form. So the way we're going to handle this is by using the next theorem, which is the squeeze theorem. Now in Cal 1, I know we talk a little bit about the squeeze theorem. Here we're going to hit it again, all right? But now we're talking about it in terms of sequences. So what the squeeze theorem says is that if you can somehow, like let's say you're trying to figure out what some sequence B sub n does, all right? So let's say we're trying to figure out what this does. As long as we can find a sequence that's smaller than it and bigger than it, then as long as these two sequences go to the same number, the sequence in the middle must do the same as those two. So I have a visual that will make this hopefully more clear. So it's saying, say that we don't know what B sub n's doing, okay? We don't know what it's doing. It's, you know, we got a sequence, dots everywhere, right? But what we can say is that we have this C sub n sequence that's always bigger than that B sub n we're looking for. And then we have this A sub n sequence that's always smaller than the sequence we're looking for. Then as long as this set of inequalities, this string of inequalities is true, then as long as these two sequences on the ends go to the same place, then the sequence we're looking for must be squeezed in between those two. Yes?
What do you mean the sequence is smaller?
Below it. Lower than it. Smaller, less than or equal to it. So think about like the y values. This y value is always smaller than that one. This y value is smaller than that. This one's smaller meaning lower. And then the C sub n is there, it's always above.
Yeah, so the red line is always in between those two.
The red dots are always between the blue and the purple. And so as long as the blue and purple go to the same place, and the red always has to be in between, then we can be assured that the B sub n, the red ones, will also go to that same answer. Does that kind of like make sense logically to you? So let's go back to the problem that I was trying to do here. Where was it? Right here, right? Trying to figure out what this is doing. And so what I'm going to do is play with this sequence a little bit. And I'm going to see, can I squeeze it between two sequences that I actually know what they're doing, right? That I actually have an idea of what they're doing. And the way I'm going to do this is to step to the side and use a property that I know about sine. I know for a fact that sine of anything, doesn't matter what it is always between -1 and 1, right? That's true? Always, that's true. That's just pre-cal. And if I know this is true, then that almost looks like that, except that has an n squared on the bottom, right? So what I can do here is I can divide everything by n squared. Now I'm allowed to do that because, well, we have to be careful with inequalities, don't we? I was helping my daughter with her homework. She was doing inequalities, and she was multiplying both sides of the inequality by a negative number, which requires you flip the sign, right? So this right here is okay because n squared is always positive, so I don't have to worry about any flipping inequalities, right? So I'm allowed to divide through by n squared, and this is not going to change anything here. And that right there is actually what I was trying to get, is this thing between two things, right? Now my hope is that I know what these go to, right? Like I need these two to actually go to the same place when I take the limit and let n go to infinity. So let me do that formally now. So this inequality is true. So I have squeezed the sequence I'm interested in between two other sequences, right? And now I'm going to take the limit of all of them. The limit as n goes to infinity of -1 over n squared must be less than or equal to the limit as n goes to infinity of sine n over n squared, which must be less than or equal to the limit as n goes to infinity of 1 over n squared. And luckily for us, this heads to where? 0, right? 1 over infinity, fixed number over something gets huge. That should go to 0. And I really hope the other one on the other side goes to 0 as well. Does it? Yeah, that goes to 0 as well. And so if these two go to 0, then that limit it must also go between 0 and 0, and the only number between 0 and 0 is 0. So that one must go to 0.
That's what I was going to ask. I was like, let's be kidding 0.
Yeah, so the important thing is that it's less than or equal to, right? So it has to be either smaller than or equal to this. So it could be equal to 0 or smaller. And this has to be bigger than or equal to 0. So to be bigger than 0, bigger than or equal to 0, and then also less than or equal to 0 means you have to be 0. Okay, so by the squeeze theorem, this goes to 0. Remember we used the arrow last class to represent that limit? If we say the sequence with an arrow to a number, we're saying that the limit goes to that number. Or the sequence goes to that number as we let n go to infinity. Okay, so that's squeeze theorem. Good, 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 good. Okay. Now, another theorem. If the absolute value of a sequence goes to 0, then the sequence goes to 0. So if you're looking at a sequence, and maybe it has some negatives and positives in there or something, if you take the absolute value of it, which would make everything positive, if that sequence goes to 0, then the sequence without the absolute value must also go to 0. So this is a theorem, so that's a proven statement. So here's an example. Look at that one right there. Be careful, that's not the one we just had. We had this one just a second ago, right? Negative 1 over n squared, that's what we had? Yep. That's not what that is, right? Because for that one, that alternates, doesn't it? Sometimes it's positive, then negative, then positive, then negative. This one was always just negative. So we weren't doing that a minute ago. So let's see what happens as n goes to infinity here. Well, let's just look at the sequence itself before. Let's just start writing out some terms of that sequence. What's the first term of that sequence? Negative 1. Yeah. So if you plug in 1, you get negative 1, right? Plug in 1 here, plug in 1 there, you get negative 1 to the first power over 1 squared, so you get negative 1. What if you plug in 2? You get 1 on top this time, and on the bottom 2 squared is 4. And the next one, 3? Negative 1 over 9. One more. Plugging in 4? Positive 1 over 16, and then so on and so forth, right? And we're asking ourselves, what does this go to? Does it converge or diverge? Does it head to a number or not?
It looks like it's going to 0.
It looks like it's going to 0. Let's prove it, though. Well, to prove it, I'm going to use the theorem. All right? I'm going to use the theorem. The theorem says that if I take the absolute value of the sequence, if it goes to 0, then that goes to 0. So I'm going to say, let's take the limit as n goes to infinity of the absolute value of negative 1 to the n over n squared. But that equals the limit as n goes to infinity. All right, let me think about the absolute value. If I plug in an n here, and then I take the absolute value of that, what's it always going to be? Positive 1. So I know that the top's always positive 1. And then the absolute value of n squared, the absolute value is irrelevant, right? Because n squared is always positive, so taking the absolute value of a positive number doesn't really do anything, right? So this just becomes 1 over n squared. And we already know that that goes to 0, doesn't it?
Yeah.
Right? So since this goes to 0, right, since the absolute value, the limit of the absolute value of the sequence goes to 0, by the theorem, right, by the theorem we just had, which is 8.1.15, we know that the limit, oh no, I'll just write it this way. We know that negative 1 to the n over n squared must also go to 0. Yes?
So I understand how the theorem works, but I don't understand why you wouldn't be able to solve this just without using the absolute value.
Okay, let me explain. So the reason why we need the absolute value is because if right here I let n go to infinity, what does the bottom go to? Okay, what does the top go to? You can't say what it goes to because as n goes to infinity, this keeps switching back and forth between 1 and negative 1, right? So you can't say it's 1. You can't say it's negative 1, right? You can just say it keeps switching back and forth, which means that limit on top, this doesn't exist. Yeah, but that's two different things, right? In order to say it's going somewhere, we have to say it's headed to one number and one number only.
Because there's no way to like split it.
But then you're not letting n go, you're making conditions, right? You're saying if n is even, then it does this, and if n is odd, it does that. But that's two different scenarios.
Well, if they both go to the same thing, could you not do that?
But it's not two different. It's not two different things, right? It's not two different things. You can't just pick the pieces of a sequence you want out and look at that, and then other pieces. You have to look at it together. Yes.
So you use the absolute value because that's a negative one. Like if that was a 1 1, like we have to do something else?
If this was 1 to the n, then it would just be 1.
Okay.
Because remember, don't confuse this with, I think you're confusing it with this, the idea of like 1 to the infinity.
Yeah.
Okay, so when we were studying this, we were studying things where this base was headed to 1, going to 1, right? And the exponent was going to infinity, like this. Limit, n goes to infinity, 1 plus 1 over n to the n. Here's an example. So as n goes to infinity, that goes to what? 0. It's getting smaller. What's 1 plus 0? Close to 1, right? Close. We never get there.
Yeah.
And then this is headed to infinity. This is 1 to the infinity, right? This is indeterminate form. That's different than me writing down 1 to the n. If I just write down 1 to the n, this is not approaching 1, that is 1. And 1 to any power is 1. So that would just turn into 1 over n squared, and that's just going to go to 0. Yeah? I'm glad you brought that up, because I remember it was years ago, I had a student who was a former Cal 2 student of mine call me up like 4 years later, 3 years later, and he's taking some class, and maybe it wasn't 4 years after, maybe it was like 2 years after Cal 2. And he calls me up, he's like, hey, I just want to let you know, you told me that 1 to the infinity was indeterminate. I mean, literally, he was like mad at me. I'm like, yes, I did. I said, but it's in the limit that's happening. If this is happening in the limit, we're not saying that this is 1. We're saying it's close to 1. That's headed to infinity. Then it's indeterminate. He was working on a problem where it was actually 1 to a power that was getting bigger, and he wanted to do indeterminate. So it's a distinction we have to make. This is all within the limit, where something like that is that's just 1. Yes?
So out of curiosity, so the theorem says that if it's the absolute value,
Mm-hmm.
it's equal to that. But my other question is, how are they conceptually equal? One is restricting it to only the positives, whereas this one is all the negatives.
Okay, be careful with what you said. You said if the absolute value is converging, then the other one is. They have to both be going to 0. Sorry, this has to be going to 0. The theorem doesn't work if it goes to something other than 0.
Oh, okay.
So you're asking, blank space, here we go. So if I were to show you those two sequences, right? If I were to plot them, okay, the first one, this -1 to the n over n squared would look like this. We said when we plugged in 1, we got what? -1?
Yeah.
And then it was 2, we got 1/4 positive, right? And then negative, and then smaller, 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 right? Like that. Okay, this one, when we took the absolute value, all it did is just brought everything that was negative up, like that. So now it's doing this, right? So if this one goes to 0, that one goes to 0 is what we're saying.
Okay.
That's all we're saying.
I actually see it now.
You see it? So even though it's scattered like this, positive and negative, it's tapering down to nothing. We have to have it going to 0 though, right? I mean, that's the condition of the theorem. So if I had something like, here. How about this? This sequence. Simple example. Can we use the absolute value on this one? So if I take the absolute value of that, what do I get here? What's the absolute value of -1 to the n? This is just 1, right? That's just 1. So what does that sequence look like? You plug in 1, you get 1. You plug in 2, you get 2. Plug in 3, you get 3, right? It's just this. Is that converging? Yes?
Yes.
What does it converge to? 1. Okay, does that mean that converges to 1? No. The theorem says this has to go to 0, and then that goes to 0. See, because this one here looks like this.
Oh, yeah.
See, it's not like funneling down to anything. It's just back and forth.
Is that technically divergent?
That's divergent, yes. Okay, good questions. Let's keep going though. All right, another example. N factorial to the n. That's completely wrong what I just said. N factorial over n to the n. Limit, n goes to infinity. N factorial, we talked about that last time, gamma function, right? Weird, I had 60 views of that video from last class.
This is your big break.
60, and it was the camera view from here. The video sucked. But I had 60 views of it. I never have 60 views. I'm just curious why. Weird, huh? It was that good, huh? Is that good? I might have posted it to the wrong playlist or something. I'm not sure. Okay, so, but I thought it was maybe the gamma function because I was talking gamma function in there. Because a lot of times Cal 2, we don't talk, like, I don't know anyone else who talks about the gamma, you know? All right, so look, when I'm seeing this, first of all, that theorem we just used is irrelevant because there's no negatives in here, right? I mean, so that theorem isn't going to matter. That theorem is only important if you got some sort of like alternating happening or negatives appearing, right? And I know I'm never going to be able to use L'Hopital.
No.
Why?
Because of the exponent.
Because of the factorial. You can actually take a derivative of n to the n. If you had to, you can do it. It's the same way you take the derivative of x to the x, and that requires logarithmic differentiation in Cal 1. So this is a little bit involved. But we could handle the derivative of the bottom if we needed to. But you can never do the derivative of a factorial because factorials cannot be extended to the real numbers. So I can't turn the factorial into like x factorial and then take a derivative. Unless we talk gamma, we're not talking gamma though.
So for this one, would you have to like kind of just prove it by kind of writing out n factorial and trying to prove if it's like has a greater or weaker rate of change in the bottom?
Yeah, we're going to have to analyze this. That's what we're going to have to figure out what's going on here. All right. So if I try right now to let n go to infinity, n factorial, infinity factorial that's just getting bigger and bigger, isn't it? Like 2 factorial, 3 factorial, 5 factorial, right? 10, 100 factorial. And the bottom n to the n is getting bigger as well. So we have infinity over infinity. But again, no L'Hopital, right? L'Hopital can't save you here. So I'm going to do something else, and this is going to be very unnatural, very weird. You're just going to see it and go, oh, wow, okay. Never thought of that, but now I see that. Now I know I can do that. It's a new tool in my toolbox. Yeah, I'm just going to analyze what's going on here. I'm going to write n factorial by its definition. Right, this is the definition of n factorial. And I do that all the way till I get to 1, right? That's what n factorial means. I'm not even taking the limit right now. I'm just looking at this expression. And then on the bottom, what does n to the n mean? N times n times n times n times n times n. How many n's? N of them, right? So let's just see. If I had, just as an example, if I had 5 factorial over 5 to the 5 as an example of this, this would be 5 times 4 times 3 times 2 times 1 over 5 times 5 times 5 times 5 times 5. Right, that's what I would have? That's the idea I'm doing here, but for n. So I'm going to have an n under each one of these, I'll have an n, right? So n here times n there times n there times n there times n, 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 all the way to my last n right there. Dot, dot, dot. Y'all agree with that? I'm going to see if I can squeeze this. I'm going to try squeeze theorem here. So here's one thing I can say for sure. This has got to be greater than or equal to 0. Now, I know that that's not a sequence, but it actually is a sequence. It's the sequence 0, 0, 0, 0, 0, 0, 0, 0, 0. Right? That's just the sequence that always spits out zeros. Do y'all agree that I can say this? I mean, this is either greater than or equal to 0. There's never any negatives here. Yes?
Because we only use natural numbers?
Yes, that's because we're only using 1, 2, 3, 4, 5, 6, right? Okay, so if I were to take the limit of this, right, take the limit, I would get 0. So what I'm hoping is that maybe I can go on this side and get something over here that's going to go to 0 also. So let's see if I can convince you of this. Do y'all believe that this is true?
Yeah.
The factors are.
Yeah, that's-
Convince me.
Well, because that's what it goes to.
You want to convince me?
So in factorial, you have one n, and then the factors progressively get smaller and smaller. Whereas in just the regular n, you have n factors that are always remaining.
Always the same.
Yeah.
Okay, so I'm going to rephrase that in a different way. Do y'all agree that this right here is always going to be the number 1? That first piece, 1 over n over n. I erased it, but that would be the 5 over 5, right? Okay, the next one would have been 4 over 5, right? So do y'all agree that this number right here is smaller than 1,
Yeah.
right? You can tell, n minus 1 is less than n. So that number should be less than 1. Same argument for this one. That's less than 1 also, right? What about the next one? Less than 1 as well. Right? Less than 1. And that would be the case for all of these, right? And when I get to this very last one right here, I'm not going to touch that one, okay? So everything in front of this, all of these numbers together are the number 1 and then a number smaller than 1 times a number smaller than 1 times a number smaller than 1 times a number. What can you tell me about this whole thing right here? It's less than 1. Because when you take a number smaller than 1 and you multiply it times a number that's smaller than 1, it gets even smaller. Right? So this is less than 1. And so if I take a number that's less than 1 and I multiply it times 1 over n, I will be less than or equal to just 1 over n. Well, that's it. I'm done. I hope that convinced you. Yes?
So, I know like infinities are kind of tricky, so how do we know that these two infinities are like a 1-to-1 ratio? Because I know that some infinities are more dense or less dense than others.
In this case, the infinity we're talking about is the counting numbers, right? We're talking about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're not trying to like traverse our way through like the numbers through like real numbers. It's the natural numbers.
Since they're counting numbers, we can assume that it is a 1-to-1 ratio.
That's right. This ratio will always be. But actually, these don't even have to be real. Like, they have to be positive, but they don't have to. Well, yeah, we need them bigger than 1, because then if it's less than 1, it gets tricky. But yeah, just to answer your question, though, we're letting n go to infinity through the natural numbers.
Yeah.
All right. So y'all convinced? All right. Now just take the limit. Now, I'm not going to actually write the limit. This time I'm going to use the arrow. The arrow, this converges to 0, right? If I take the limit of that as n goes to infinity, I get 0. Over here, limit n goes to infinity of this, I get 0. And I've squeezed this between these two, right? And they both go to 0. So that means that this goes to 0. Yes?
So I understand that like like you split up the fraction into like these little fractions to represent it goes from 1, smaller than 1, smaller than 1.
Yeah.
But how do you end up with it's less than or equal to 1 over n? Like how do you get that specific?
I said just ignore that. That's the number 1, right? It's gone. Each of these is smaller than 1, right? So what happens when you take the product of two numbers that are smaller than 1? You're still smaller than 1.
Yeah.
All of these are smaller than 1. So this right here is 1 over n with some number in front of it, some constant in front of it, let's just say, but that number is smaller than 1. The constant in front of this one is 1. So a number that's smaller than 1 in front of this is less than or equal to the number 1 in front of this. 0.8. 0.8 times 1 over n is less than or equal to 1 times 1 over n. That's what we're saying.
Yeah.
This is like a coefficient in front of 1 over n. That coefficient is smaller than 1. So that coefficient smaller than 1 in front of this is smaller than or equal to the coefficient of 1 in front of all of that, in front of 1 over n.
I get it.
Got it? All right, a sequence you should know. R to the n. I'll give you a specific example here. A couple of examples. Let me give you a couple examples. 2 to the n. That's an example of this. This would be the sequence 2, 4, 8, 16, right? Keeps going. These are all powers of 2. Another example. A sub n equals, let's go 1/3 to the n. This is the sequence what? 1/3, 1/9, 1/27, dot, 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 right? Keep going. You get the idea. The r is the base, and then the n is the exponent. So we could use any number we want as the base, any number we want. This result, okay, now I'm not going to prove this because time, we just don't have enough time, okay? So please, if you want to go through this, we can do it in my office. If you ever have something like that, we have conclusions that we don't have to prove in here, we can just deduce, we can just use this note, okay? If we're trying to take this limit, we're going to get one of 3 answers. We're going to get 1 if r is 1. Okay, so does that make sense to you? If I put 1 right here, 1 to the first, 1 squared, 1 cubed, 1, it's just 1, 1, 1, 1, 1, that converges to 1. So if r is 1, you just get 1. Now, if the absolute value of r is less than 1, that would be something like this. Or let me give you another example of that. A sub n equals negative 1/4 to the n. Do you see the r here? Negative 1/4. The absolute value of that is less than 1. This will converge to what? 0. And you can kind of think about what's happening to this, right? They're getting smaller and smaller. Now they are switching back and forth positive and negative on this one. Right? This sequence is negative 1/4, positive 1/16, negative 1/64, dot, dot, dot. Right? You take that to the first power, square it, cube it. Do you see these are getting smaller and smaller? So if the absolute value of r is less than 1, you get convergence. And if the absolute, well, otherwise, okay, if r is not 1, and the absolute value is not less than 1, so if like r is 2, you're going to get divergence. Do y'all agree that diverges? See what's happening to it? 2, 4, 8, 16. That's just going to what? It's getting infinitely big, right? For convergence, we need it to go to a number. Infinity is not a number, right? Infinity is an idea, right? So, that okay? Do I need to go into more detail about that? I think I put some examples down here for us to see. Examples of, this isn't, yeah, this just shows I can change the value of r, and you can see what happens to the sequence. So if I make r small, it converges. If I make r bigger than 1, it diverges. Fun, fun. Okay, increasing, lots of definitions here.